Welcome fourth graders to the Dallas Independent School District STEM Environmental Education Center. We'd like to give a special welcome to the schools who are with us live this morning. We have students from Martin Weiss, Arthur Kramer, Nathan Adams, and Seagoville Elementary with us this morning. Thank you so much for joining us today. If you are watching this and have not registered for this field trip yet, you can still do that by going to www.tiny.cc/3-5 registration to get yourself or your class registered for this virtual field trip. We just use that information for our attendance purposes. And today's program is going to be all about mixtures. During this virtual field trip, students will compare and contrast a variety of mixtures, including solutions. So we're going to explore some mixtures with Mr. Mirez, and then we're going to explore even more mixtures with Mr. Dominguez. Then we're going to move into solutions. So we're going to explore solutions with Mr. Monroe, and then explore more solutions with Ms. Schramm. While we're doing all of that, if you have any questions for us, you can go ahead and ask those. But since this is a virtual field trip, the way you need to ask a question is www.tiny.cc/question-answer. Once you visit that website, you'll fill out a super short form to submit any questions you have about mixtures or solutions to us. You can ask as many questions as you like, and we'll do our best to answer all of them in the time that we have with you this morning. So let me stop sharing my screen here and turn things over to Mr. Ramirez, who's going to get us started off with mixtures.
Hello, my name is Ms. Ramirez, and in this segment, we're going to be learning about mixtures. So before we get started with what a mixture is, I'm going to show you a common example of a mixture that we use here at the Environmental Center. So this is a mixture of sunflower seeds, corn, and oats, and then also some mealworms and a superworm in there as well. Now, I'm fixing to show you guys an animal friend, and this animal friend loves to eat a mixture of these two things. So this animal friend is an omnivore. This animal friend has a beak, feathers, and cannot fly. So go ahead and make a guess on what this animal friend is, and I'm going to go ahead and pull her out while you guys are guessing. If you said a chicken, you would be correct. This is Pepper the blue silky chicken. And she gets that name because she has a patch of blue skin around her ears. And when you touch her, she is super soft like silk. Now, she loves to eat a mixture of seeds and insects, whether they are alive or dead. But that is just one example of a mixture out here at the Environmental Center. So let's talk about what exactly a mixture is. So a mixture is just a combination of two or more substances that keep their individual identities. And neither substance has become something new. Most of our mixtures can be separated rather easily depending upon those physical properties. So physical properties would be things like color, size, melting point, density, magnetism, size. They're just substances, properties or things that help us to separate a mixture. Now, today we're mostly going to be focusing on heterogeneous mixtures, and that just means that these mixtures, you can clearly make out those individual mixture. So I'm going to go ahead and share my screen with you guys, and we'll start a quick presentation. I do have a couple of questions that I want y'all to keep in mind. Hopefully by the end of this presentation, you'll be able to answer these two questions. The first is, what are the characteristics of a mixture? And the second is, what are two examples of physical properties? And what are two tools that we can use to separate a mixture? And here on the right, we have one of my favorite examples of a mixture that I love to eat. It's a poke bowl, and it's Hawaiian, but it actually uses some Japanese flavors and cuisine. And it's essentially, poke just means chopped or sliced. So it's a variety of mixed meats like chicken and crab, and as well as chopped vegetables. So it's all mixed together. This would be a great example of a heterogeneous mixture. You can clearly make out those individual ingredients. So think about some of those mixtures that you guys love to eat and see if you can give some examples. So again, a mixture is just a combination of two or more substances that keep their identities. Neither has become a new substance, and most can be separated fairly easily using those physical properties. So I'm going to show you some other examples of mixtures at the Environmental Center. The first one that you're going to see is our cat eating a mixture of cat food. So you can clearly make out the individual flavors. Here are two bunnies eating a salad mixture. So again, it's heterogeneous. You can make out the individual components, and it can easily be separated. I can clearly take out those big chunks of carrots or apples and separate it. There's Pepper, our chicken, enjoying her mixture of pellets and mealworms and fruits and veggies. These are box turtles enjoying their salad mixture. You can see the okra, the cucumber, the apples, the carrots. Probably the easiest way to separate that one would just be by hand. And then here's another example of a mixture. Teachers, feel free to pause the video to allow students time to discuss and brainstorm. But my question for y'all is, how can I separate this mixture of paper clips, pebbles, sand, and tree bark? So think of those four things. What are some physical properties that we can use to our advantage to help us separate that? Again, feel free to pause the video so students can formulate a plan and maybe identify some science tools they want to use, but I'm going to go ahead and move right into it for the sake of time. So again, we have the paper clips, the sand, the tree bark, and the pebbles. I'm going to give you guys a hint. I'm going to show you some of the tools I used. I used a magnet, a sieve sort of like a mesh net or a strainer, and then I used a container of water. So those were my science tools. So my first thing that I decided, I had a question: how can we separate the paper clips from the other materials? So think about the physical properties of a paper clip. What can we use to help us separate those paper clips? Hopefully you guys thought of a magnet. You can even use a refrigerator magnet that you might have at home. So paper clips are magnetic. We are taking advantage of that physical property to remove those paper clips. Now, all that we're going to have left are the rocks, the sand, and the tree bark. So my next problem is, how can I separate the smaller sand from the other materials? So we're thinking about the physical property of size. So what science tool can help me separate something by size? And hopefully you guys said some sort of sieve, a net, a strainer. I know at home when I'm cooking pasta, I use a colander to separate the water and my pasta. So here we have our mesh strainer. I'm going to pour our mixture through it. And because the sand is so small, the sand will go right through those little mesh openings, leaving the big stuff at the top. So you can see the sand falling through. Again, we are separating by the physical property of size. So now I have the small stuff in the bucket, and I have all the big stuff, the rocks and the bark, left. So my last question is, how can I separate those heavier rocks from the lighter bark? And I'm going to leave y'all to think about that, and maybe y'all can experiment with that one at home. So I have the rocks and the lighter bark. What can I do to separate those two? And then I have a challenge question for y'all. I would like for y'all to go on a scavenger hunt, find 5 examples of mixtures at your home or school, and explain why each is a mixture. I also have a couple of thinking questions. So here's a little picture of a salt water solution. It's simply salt that's been mixed in with water. So can a solution also be a mixture? Try and think about that. And then my other one, here I have some lava lamps that you might have at home. Think about, can mixtures also be liquids as well? So I'm going to go ahead and stop my screen share, and I have one last thing to show you guys that y'all can do at home. If y'all have water and cooking oil, all you have to do is just put them inside a bottle. So I have my water that I dyed with food coloring, and then I have oil so that parents might cook with, mixed in some beads, and now you have a special type of heterogeneous mixture called an emulsion. So an emulsion is a heterogeneous mixture like this, and it's a mixture of two liquids that don't disperse together and they don't typically combine. So the water and the oil is not mixing together. And think about how might you separate this emulsion. Other emulsions that you guys might think of, I know I like to eat salad sometimes. I'll put the vinaigrette. That's also an emulsion. So I'm going to go ahead and give it back to Mr. Broughton to answer any questions.
Thank you, Mr. Ramirez. Sienna asked, can you separate a box with cereal and raisins? And what would you use to separate it? If I had to separate cereal from raisins, I would probably just use my hands. Sometimes you can use a tool like a magnet or a screen to separate things, but sometimes your hands work best. And then London asked, what are some other ways to separate mixtures? And that is the perfect question for Mr. Dominguez to answer, because he's going to show us some other ways to separate mixtures.
Hola amigos, en esta porción de su paseo virtual vamos a hablar un poquito más sobre las mezclas y cómo separar el contenido de esas mezclas usando propiedades físicas. Y la propiedad física que vamos a usar, o las propiedades físicas que vamos a usar, son la propiedad física de flotabilidad y la propiedad física de conductividad. So guys, in this portion of your virtual field trip, I will be talking to you guys a little bit more about mixtures and how to separate the content of those mixtures using physical properties. And the physical properties that we are going to use today are the physical properties of buoyancy and conductivity. So I have Kiwi here, and she loves mixtures of leafy greens and worms, well, different types of worms, mealworms and waxworms, all that good stuff. So while I make her a salad, I'll go over the definition of mixture one more time, all right? So let's get started. All right, guys, let's remember that mixtures are a combination of different things that can be easily separated. So when you mix these things together, their physical properties, their individual physical properties don't change. So for example, kiwi salad has some zucchini. It's got different types of lettuces, and it's pretty easy to separate all these things. It's got some worms. You want a worm? She doesn't want a worm right now. Let's see if she wants one. Do you want one? No, I don't think she wants one at the moment. But that is the basic definition of a mixture. Okay, amigos, acuérdense que las mezclas son una combinación de dos o más cosas que se pueden separar fácilmente. Por ejemplo, esta calabacita la puedo quitar y es bien fácil separarlas. Estas lechugas puedo separarlas. Las espinacas las puedo separar fácilmente, y hasta los gusanos se pueden separar fácilmente. Y cada ingrediente de esta mezcla retiene sus propiedades físicas. ¿Okay? Vamos a ver si le podemos dar un gusano a Kiwi. ¿Quieres un gusano, Kiwi? A ver si se lo come. No, no lo quiere. Ok. Pero acuérdense que esta es la definición básica de una mezcla. Ok. La primera manera que vamos a usar para separar una mezcla, los contenidos de una mezcla, es usando la propiedad física de flotabilidad. Entonces, todo lo que necesitan, y esto lo pueden hacer en la casa o en la clase, es una bolsita de una mezcla. Pueden ser diferentes cosas. Yo escogí unas botanas. Tenemos un poquito de chocolate, de almendras, de cacahuates, galletas saladas, diferentes cositas. Y quiero saber cuáles de estas cosas van a flotar y cuáles no. Eso me va a ayudar a separar esta mezcla. Todo lo que necesitan es, claro que ya les dije la mezcla, un plato hondo y un poco de agua. Entonces primero voy a llenar el plato hondo con mi agua. Alright guys, so like I was saying in Spanish, what I want to do is I want to separate this mixture using the physical property of buoyancy. So I chose different things, and you guys can, make your own mixture. So I made my mixture out of pretzels, some Chex Mix, some trail mix that has peanuts, raisins, all that wonderful stuff. And what we're gonna do is we're gonna dump all this and see what items have buoyancy or a higher buoyancy, which will make them float and which ones will sink. Okay, vamos a empezar. Vamos a ver. Ya miro que hay algunas cosas que están flotando. Los cacahuates sí flotaron, pero los chocolates no. Qué interesante. Vamos a ver si una almendra flota o no. Oh, sí, la almendra flotó. Entonces, amigos, esta es una manera que pueden usar para separar los contenidos de una mezcla. So, like I said, guys, this is a really easy way of separating a mixture using the physical property of buoyancy. And what's really good about this is that you can also infer which items have a higher mass or a higher density than other items. So those chocolates have, even though they're the same size as the peanut, have a higher density, and that's why they sank. Pretty interesting stuff. All right, guys, the last way that we are going to use to separate a mixture of different matter is to use the property of conductivity. And what you see here is a simple circuit. At the moment, it's not complete, so that's why you don't see the bulb on. But if I complete my circuit, you will see that it turns on. You guys see that? So it's on right now because the circuit is complete and there's electricity flowing. And here's my power source, the battery. Let me disconnect these two wires. And what I'm going to do is I am going to see which of these different pieces of matter, which of these is going to complete my circuit and let electricity flow. If the matter allows electricity to flow properly, the light will turn on and it will tell me that it's a conductor. If it's not, it'll be an insulator. All right, so we'll start off with a rubber band. Do you guys think this will let electricity flow efficiently? Let's see. All right, so let's hook this up to this end. And then let's see if our light turns on. Did it turn on? It did not. So this part of my mixture of different matter is not a good conductor of electricity. All right, so let's put it off to the side. All right, let's try the metal wire. What do you guys think? Conductor or insulator? We'll see. All right, so let's hook this up to this end. Let's hook this up to this end. Hey, what do you guys, there we go. You guys see that light? It turned on. So this piece of wire is a good conductor of electricity. So let's put this off to the side. And last but not least, we have this piece of yarn. Let's see if it conducts electricity. What do you guys think? Yes or no? All right, so let's hook this up to this end and then this end. And unfortunately, my yarn is not a good conductor of electricity. All right, guys, I hope that you guys learned a little something about mixtures and a couple different ways of separating the contents of those mixtures. All right, guys, have a wonderful day.
Thank you, Mr. Dominguez. Stephanie asked, will all metal conduct electricity? And I don't want to answer that because that is something you could try at school or at home to see if all metal does or does not conduct electricity. So we have learned about mixtures and how to separate various mixtures using things like our hands, but also some tools. But now let's get into solutions with Mr. Monroe.
Good morning, students. My name is Mr. Monroe, and we're going to be looking into solutions. When we talk about solutions, we're talking about a specific type of mixture. You know, solutions can be a combination of gases, liquids, and even solids. Now, today, and a good example for us to be thinking about is seawater. Seawater is a solution of solids that have been dissolved in the liquid, which is water. Now, in this condition, water is considered to be the solvent. The solvent is the substance present in the largest amount, and the soluble is the actual solid that is going to be dissolved in the solvent. Now, I did a study last week, and that study was on separating a solution. And the particular solution that I was working with was H2O, water, with the soluble of sodium chloride, which is salt. Now, the tool that I'm going to be using to extract the salt from the H2O is a natural process that happens on our planet. It is the process of evaporation. Now, evaporation occurs naturally, and it occurs in a particular cycle that I know you guys have learned all about. It's the water cycle. Now, we have in that water cycle, that's the way our fresh water is replenished. Evaporation is the changing of the liquid into a gas. That gas form is called water vapor. It's around us already, but it's invisible. Now, once a certain condition exists in our atmosphere, that gas form, which is water vapor, is going to change back into the liquid form and hopefully fall back to the earth in some type of liquid form that we refer to as precipitation. And if the air temperature is below freezing, then it's frozen precipitation. So, you know, one of my concerns was when I was in college, I had to read a book about the future. And we had to respond to some of the things that we found in that book. Well, one of the things that really concerned me was the fact that our world population of people is constantly growing, and yet there is no new water in the world today. So my fear was that someday we may run out of water. And I kept thinking, I said, well, could we make some type of plants or factories that would convert salt water into fresh water? And you know what? I kept thinking and thinking and thinking, and we already have something going on, and that is the water cycle, okay? So listen, I was glad to do this little field study. And this field study helped me to understand something about that natural process that we call evaporation. Now, several conditions existed in my field study that we created. We wanted to separate that solution that we call water mixed with sodium chloride. Now, two factors I wanted to involve. One was the fact about surface area, and the other was, would temperature affect the rate of evaporation? So I put together this little field study, and rather than me keep talking, let me go ahead and show you what I did. I'm going to share my screen with you. I want you guys to bear with me while I do this, and we will get started. I did this little experiment last week. It's going to take it a little while to load. But I set up a little study. And as you can see, the area in this area is where I had set up a heat lamp because I wanted a condition to be existing there where it was a little warmer, a little hotter than normal. And so as you can see, I have a thermometer here. We use a thermometer. I have graduated cylinders here, and then I have it labeled H2O, which is just the plain water, was on this side. And then we have right here H2O with water, and we have the sodium chloride, which is a salt in the base. We also had it in the Petri dishes. Now, if you notice the graduated cylinders, there's not a lot of surface area where the actual water or the liquid or the solution is formed. But in the Petri dishes, it's all scattered out. We have more surface area there. Over here, I had these set up in room temperature. Now, the average temperature was somewhere over under the heat lamp was 93 degrees Fahrenheit. On the other side, where the heat lamp was not heating up the area, it was like room temperature, somewhere between 79 and 80 degrees. And it went very quickly. It surprised me simply because at the end of day one, there was just a little bit of water around the edges of the Petri dish. And I could see, when I put the water with the sodium chloride or the salt, I kind of swirled it to mix it. And the water, I should have taken a picture of that. It was just kind of milky color. But here I can see that there's still a little water, but the salt or the sodium chloride is starting to show up. Over here, where there's no heat, water is quite a bit of water still in the Petri dish, and we can start to see a little bit of the salt, the sodium chloride, okay? Now, the graduated cylinders, which had less surface area to be exposed, but yet the 10 milliliters of H2O was definitely a little deeper with not as much surface area. We can see that the water is pretty well holding, or the H2O is pretty well holding. Now, when it came to day two, that's when I noticed changes. On day two, there was no water in this Petri dish. It was gone. Still yet, water here. Water here. You can see that it does have a milky color, but here there is no water, and the salt, the sodium chloride, is still there. So I kept wondering, I thought, you know what, that would work perfectly. Along the beaches or somewhere, maybe we could put these plants where we could accelerate the process of evaporation. But that happens every day. It's a natural process. So we got that going on anyhow. Over here, water's completely gone. And then over here, guess what? We start to see more and more of the salt crystals. So definitely over here, everything was accelerated. So temperature did have an effect on the natural process of evaporation. And also the surface area, the wider the surface area and the shallow the water is, guess what? Evaporation happens very, very quickly. Okay, so I'm going to stop sharing my screen right now. And students, that natural process of evaporation, it happens daily. And I've often, when teaching students about the water cycle, I have mentioned that it's going to happen anyhow. Water is going to evaporate, but temperature, the sunlight is definitely going to accelerate it. And we just found out surface area is another big factor in evaporation, or the separating of that solution from the liquid, which is the solvent, to the solids, which is the sodium chloride. So hopefully I've helped you understand about evaporation being used as an extract to separate certain elements that have been put together in a solution, just like seawater. So I'm going to turn it back over to Mr. Broughton. So if any of you have any questions, I bet he can answer those for you. You guys have a good day.
Thank you, Mr. Monroe. Miss Harris's class at Martin Weiss asked, could we get fresh water from the icebergs which are melting due to the climate change? And you could, if you took ice from an iceberg and melted that, there would probably be some things in that liquid like salt or maybe some dirt that you would not want to drink. So you could then evaporate the water and leave those impurities behind and have fresh water to drink. So it's possible to do that, but do we do that? Mostly no, because it would be very expensive to do that. And we have cheaper, just as clean water sources closer to home than traveling all the way up to the North or down to the South Pole to try to get water from icebergs. All right, now we're going to explore some additional solutions with Ms. Schramm.
Hey guys, it's me, Miss Schramm, and let me get my screen going. All right. So, like Mr. Broughton said, I am focusing on solutions as well. So at the end of my little section, you'll be able to compare and contrast different mixtures, including solutions. So before I get going, I wanted to go over this Venn diagram comparing mixtures and solutions. So on the left in the red, we've got things that are true for mixtures. So mixtures are the substances within mixtures maintain physical properties. That means they are going to remain how they looked. Like when we were seeing those salads that all the little critters here at the EEC eat, you can pick out exactly, there's lettuce, there's tomatoes, there's little corn, whatever there is, you can see it. It maintains its properties. And those mixtures are easily separated. You saw Ms. Ramirez was able to use magnets, a sieve, her hands. Mr. Dominguez did sink or float. And those were easy ways to separate those mixtures. Then solutions, on the other hand, are substances that do not maintain physical properties. So Mr. Monroe showed you salt water. He mixed salt in the water, and that salt was a solid before, and it mixed right into the water and became a part of the salt water. And then those are not easily separated. You saw it took Mr. Monroe different ways of heating or increasing the surface area to separate the salt in the water to get it to evaporate. And that wasn't easy. It took multiple days. It wasn't so quick. And then lastly, the solids dissolve into the liquid. Like that salt that was a solid, then when stirred became a part of the liquid. And something they both have in common are just two or more substances combined. So solutions are just, they're mixtures, but they're more specific mixtures, okay? So they are a little bit more special. Okay, so let's see. We have our vocabulary here, and I have the definitions for mixtures and solutions again. We won't read it, but it's there for your reference. Okay, so when we're dealing with solutions, we have some other vocabulary words that we need to know. So solvent means the receiving substance. So the most common solvent that we use in science or in everyday life is water. So usually the receiving substance is water, not always, but usually. And today that will be true. We'll be using water as our solvent. Then we have the solute. That's the solid, liquid, or gas that mixes into the solvent. So that is kind of the secondary substance that's going into it. So using our example of salt water or sugar water, the salt would be the solute. It's going into the water and kind of dissolving into it. And then there we go. Our next vocabulary word is dissolve. It seems to disappear because it disperses evenly. So when something dissolves, like if you're making Kool-Aid or something, you drop the little solid powder into the water, you mix it and it becomes one. It spreads out evenly, so it's a part of a new solution. All right, so here's an example of a solution with many solutes. This is lemonade, obviously. And so the solvent would be water in that case. Then there would be sugar that you would add, and you'd stir that in, and that would disperse evenly. It would dissolve. Then you add the lemon juice once again, that disperses evenly, and you create your solution of lemonade. Okay, so Mr. Monroe talked about how we can harvest water from salt water and separate the salt and the water to get drinking water, right? But I'm going to talk about how you can use a similar process, the same process, but to harvest the salt. So my example is this picture on the left from Cabo Rojo in Puerto Rico. And this is the Las Salinas salt flats. And I was able to visit there in spring break. Unfortunately, I did not take this picture because I was not at the right season early in the spring. But they do have these beautiful salt flats that you can visit and kind of see evaporation in real life. So what they do is they kind of rake off a big flat area. You see it's kind of pinkish. The color of the salt makes it kind of pink, but they flatten that area and block it off. So all that's in there is salt water. So they let the ocean water flow in at high tide, then they block it off so that the water is kind of stuck just sitting in there. So it's like a really shallow pond. It's like probably like ankle deep, not even to your knees, very shallow. So it's very wide, because remember from Mr. Monroe, we learned that when you increase the surface area and the more water that is touching the air, making making contact with the air, the faster evaporation will go. So they've had very wide and shallow pools of salt water. Then of course we know Puerto Rico is an island. It's very hot. You could see there's barely clouds in the sky. It's very sunny there. And so it heats the water, and that also speeds up evaporation, right? So with the heat from the sun and this large surface area from the large flats, that creates the evaporation. And once all that water is evaporated, they can go ahead and scoop up all that salt, and I'm sure there's other filtration and everything to make sure it's all cleaned up, but then they can sell that salt, and we use it in cooking and every day. So I want you to keep that process in mind and that idea of mind. And I have a STEM challenge for you. And we're actually going to do it together. But if you wanted to pause the video and talk about this, that would be great. Otherwise, I'm going to scoot along and keep going. So how could you use what you know about mixtures and solutions to separate sand and salt? So I'm going to stop sharing my screen, but that's kind of the hint. So those are the materials we're going to use: is a beaker with water, a coffee filter. You can use a rubber band. You'll see why. You don't necessarily need it, but then we have our salt and our sand. Okay, so I'm going to stop sharing. Like I said, pause if you want to discuss. Otherwise, here we go. So I have my sand in one beaker, just a little bit. Then I have my salt, and I'm going to combine them. Two solids, I'm combining them. Woo, I spilled a little bit, that's okay. Then I'm going to stir them up. Now at this point, we have a mixture, right? These two solids are still separate. They did not change form, they did not change their physical properties, but they are mixed together. Now, when we were separating mixtures earlier with your other teachers, you were able to use things like magnets, sink or float, or other forms to separate them. But that's not going to work in this case, because the salt crystals and the sand crystals are relatively the same size. So I can't filter them out with a sieve. Neither is magnetic. They're both not going to sink or float. So I'm going to create a solution. So hopefully you are thinking of what I'm going to do, connected to the ocean and everything, right? So I'm going to make a solution of salt water within this mixture, right? So when I pour water in, I'm gonna have to put kind of a lot because I put a little too much sand. Okay, so I need to stir it up, right? When we're making a solution, we stir it right up. And what's going to happen is the salt is going to dissolve. That's going to disperse evenly. It's going to spread out in the water, becoming a part of the salt water. So now it's a part of the liquid. It is dissolving. Now let me stir it up and then I'll let it settle for you so you can see. Okay. So you can see the salt is dissolving into the water. It's joining the water. Now the water is a little cloudy because it is salt water. But the sand, you'll notice, did not. It did not dissolve. It is staying completely separate. It's just sitting there on the bottom. But how do we get it out? Because I want to get my sand and my salt separated out. And now we just have salt water and sand. So my next step is going to be using the coffee filter. I mentioned we would use a coffee filter. This is the part, if you're trying it at home, you might want to use a rubber band just to hold the filter in place, but I'm just going to put it into my beaker and kind of hold it. But if you wanted to, you could use a rubber band to kind of hold it like this tight. So I'm going to pour the salt water and the sand into the filter. So the salt water is going to go through the coffee filter. And the sand is going to get left behind. Now, I could try and scrape this all out and dump it into the filter, but I'm just going to let this bit dry on its own. So I'm going to set that to the side and let it dry. And then this bit in here, once all the water filters through, I'll take this off and let that dry as well. So it's going to take just a little bit of seconds. Okay, so it's pretty much all out. The rest is going to evaporate on its own. So I'm going to lay this out and let that sand dry off so the water will evaporate, and I'll have my sand over there. So now I have my salt water, but remember, I wanted to get that salt separated. So I'm going to do just like they do in the salt flats. I've got a wider area. I've got my biggest Petri dish I could find, and I'm going to pour the salt water in here. So just like Mr. Monroe taught me, I want to increase the surface area so it will evaporate faster. So I've got my wide Petri dish and a shallow water. You can see it doesn't even fill up the whole Petri dish, but that's okay. And then I want to put it in a sunny spot in the room because we know that the heat is going to help increase the evaporation rate. But I also have another idea. So just like when you're eating soup or drinking tea or hot chocolate, when you blow on that liquid, it helps it cool down faster. But I don't know if you've ever thought about why. So when you blow on it, you're actually exposing more of the liquid to the air. And that's temporarily increasing the surface area, which we already know will help speed up evaporation. So when you are agitating the water or blowing on it, that's actually increasing its contact with the air. So that will help speed up cooling something off, but it also helps speed up the evaporation. So I have a big fan in the other side of my science lab over here, and I'm going to stick this in front of the fan and help it dry. So it's going to be in a sunny spot. It's got a lot of surface area, and it's going to be in a fan. So it's constantly being agitated and churned up. All right, and that will help me separate my saltwater solution. Now, it won't be quick enough for me to finish in this last minute I have with you, but kind of as proof that it does work, I have spilled on my table and you can see it's already evaporating and forming salt crystals. So if you look up close at my mess of a desk, you can see that the salt water is starting to evaporate and you could see the little salt left on my table. So there's my proof, my accidental proof that it will work. All right, so let me share lastly my kind of parting thoughts. This is how we completed that separating the salt and sand. And there's an example from another time I did this. And okay, so my last questions for you are, we have Kool-Aid. So Kool-Aid is a solution of water, sugar, and food coloring. But my question to you is, what happens when you add ice? Is that now a mixture or a solution? So the picture on the right, is that a mixture or a solution? Then what about when the ice melts? Does it change? Is it still a mixture or is it still a solution? That's up to you. So those last two questions are kind of your food for thought, and you can talk about that with each other. I hope you had a great time on your virtual field trip. I hope to see you again. And yeah, goodbye.
Thank you, Ms. Schramm. I'm going to do a quick recap of what we covered this morning. So let me just share my screen here one more time. There we go. And today's program was all about mixtures. During this virtual field trip, students compared and contrasted a variety of mixtures, including solutions. So we learned about all sorts of mixtures and how to separate those mixtures with Mr. Mears and Mr. Dominguez. And then we learned all about solutions and how to separate solutions using evaporation and how to make evaporation go faster with Mr. Monroe and Ms. Schramm. Thank you so much for joining us this morning. We appreciate you taking the time to learn about mixtures and solutions with us. We hope you enjoyed this virtual field trip, and you can let us know whether you did or not by going to www.tiny.cc/3-5 feedback and filling out a short feedback form for us. We hope to see you again in about 3 weeks during our next virtual field trip for fourth graders. Have a great rest of your day, and we'll see you next time. Goodbye.